Obviously, I've brought along my Numberphile playing cards. Other playing cards are available, but these are the best ones. Okay, so just, well, you know our Numberphile playing cards. There's me.
Well, you put yourself
of course, I'm always at the top of the pack, Brady. There is you, of course, so they can watch. They're just here to watch. I'm also going to let Matt watch because Matt is the sort of king of Numberphile card tricks, right? So, okay, so I've just taken 9 cards. Okay, the first, all the clubs, basically, all the numbered clubs. Here's the challenge to you, Brady. I want you to put them in any order you like.
I'm not even going to pay attention. Let's go. That'll do me.
Yeah, okay. So if we read off what number that's going to be, it's 945,136,872. Do you notice anything about that number? Is there anything you notice about it?
It's even.
It is even, yeah? Do you think it's obviously not prime then? Do you think this number's in the 9 times table?
Probably not. Doesn't feel like it is.
Yeah, I mean, 1 in 9 numbers is in the 9 times table, right? So you might think it's unlikely. Should we have a bet? Okay, I'll bet you a pint, right?
Pint, all right.
So you're saying it's not. I'm going to say it is.
All right.
Okay, so should we check?
Yeah.
Okay, let's check, right? So, okay, so we put the number in, divide it by 9, see if we get a whole number. Oh, yes, we do. Okay, now do you want to go again? Do you want to try again? You can even take a number out if you want.
Any number I want?
You take out any number, right?
All right. Well, let's take out.
We'll
the
do
top.
double or quits, right?
Let's take out the top number.
Okay, you're taking out the top number, so you've been left with this number.
Yeah.
Okay, do you reckon this is in? You can rate. Do you want to move them around a bit?
Yeah, let's swap the 5 and the 4. And there we go.
You sure? Are you done?
Yeah, I'm done.
Okay. Do you think this is in the 9 times table?
Yes, I do.
You do now, do you?
Yes.
Okay, well, you might have won your bet now. Okay, let's check it. Divided by, let's see, 9 equals. Yes, it is. Well done. Well, you removed the 9, which made it a lot easier for me. If you'd removed, say, let's put this back. If you'd removed the 5, my next step was going to be, oh, well, it's only fair. I get to move one out, take one out as well. And I was going to take out the 4. We'll come back to why that worked later. Let's try another trick, okay? Slightly different one. So you've got the first 4 cards. Now, multiples of 3 are quite common, right? I mean, 1 in 3 numbers is a multiple of 3. Right, I've given you 4 cards. Right, you can put them in any order. Just make me a multiple of 3.
Well,
just try it. You can guess.
All right, let's go with 2, 1, 4, 3.
Okay. You don't sound confident, Brady. I like to see a bit of confidence. Okay, so 2, 1, 4, 3. We're going to divide it by 3. Oh dear. Right, do you need some help? I can help you. I can help. Yeah, I'm just going to put one card in for you, right? This one. I know you can put it whatever you like.
Oh, but let's put it in the middle.
Okay, let's put it in the middle, right? You want to put it right in the middle? You sure? You don't want to put it over here?
No, I'm going to put it in the middle.
Okay. All right. Well, let's turn this card over. Okay. Now let's see if this helps the situation. Okay, let's try it now. 2, 1, 5, 4, 3. Let's try dividing that by 3. It worked. Okay, so what is going on, Brady? What is going on? Well, these little tricks, well, they're kind of inspired by actually my own incompetence. Because in our last video that you and I did together, which was about Belfiger's prime, if you remember, we asked the following question. We asked, is this number, we had a 1, and then lots of zeros, and then a 616, and then another bunch of zeros, and then a 1. We asked if this number was a prime number or not. We said, if we put in enough zeros, can we find a prime number? And I ran a little computer code and got up to 100,000 zeros and didn't find any. I don't know if you remember this. And I searched up to n equals 100,000 and no prime numbers. And of course, our super smart Numberphile viewers immediately saw that this was never going to be a prime number. And the reason was, well, if you calculate the sum of all the digits, okay, so the cross sum of this object, then you'll get a 1 plus lots of zeros, plus 6 plus 1 plus 6, bunch of zeros again, plus 1, and that totals 15. Now, 15 is divisible by 3. And if that number, if the cross sum is divisible by 3, then it guarantees that the original number is divisible by 3.
So you were running this code, checking every number when you were never ever.
It was never going to be there. It was never going to be there. So waste of computer time and brain time. I should have just been as smart as the Numberphile viewers, right?
Why didn't you think of that? Or was that like?
To be honest, if I'm honest, I was trying loads of different things because I wanted something that might sort of look cool in the video. And I got so sort of hung up on all the different things I was trying, I sort of lost sight of the beauty of maths. So of course, this explains what went wrong with your attempt at the number earlier, right? Okay, you took the first 4 numbers, whatever combination you take these in. I mean, these numbers 1, 2, 3, and 4, they add up to 10. So whatever order I put them in, the cross sum is always going to be 10, but 10 is not divisible by 3. So whatever number I create cannot be divisible by 3. And now I add the 5, and it doesn't matter where I put it, the cross sum is now guaranteed to be 15. Whatever number I create is guaranteed to be divisible by 3. Okay, if the cross sum is divisible by 3, the number is divisible by 3.
Okay.
It's also true for 9s. If the cross sum is divisible by 9, the number is divisible by 9. And that comes back to this one. First 9 numbers, what do they sum to? They sum to 45. 45 is divisible by 9. So whatever combination of these numbers I take, whatever order I take, it's guaranteed to be divisible by 9.
This isn't true for other cross sums. Like if the cross sum is divisible by 4,
no,
it doesn't mean the number.
No,
it's just 3.
3 and 9, it works for. Okay, it works for 3 and 9. Okay, there are other rules that you can apply to other numbers, and we'll get into that. But for this cross sum rule, it works for 3s and 9s.
Let's see a proof then.
Okay, let's see the proof. Let's write down the kind of number that we might be interested in. Let's just write it down as follows. So the number n, let's just write it. It's going to be an n plus 1 digit number. Okay, which we might write like this. Okay, so we've got A0 in the 1s, A1 in the 10s, and so on. Let's actually write down what this number is sort of algebraically. So this means that n is really 10 to the n times an plus 10 to the n minus 1 times an minus 1 plus 10 a1 plus a0. Okay, so that's what this number is. Okay, any number in principle at this stage. Now let's write down the cross sum. Okay, so the cross sum is easy to write down. Let's call it T of n. Okay, that's just going to be the sum of all these individual positions. So an plus an minus 1 plus all the way up to a1 plus a0. Okay, now let's do that, take away that. Okay, we do that, we get n minus t of n. Okay, let's see what we're going to get. So in this position, we'll get 10 to the n minus 1 an plus 10 to the n minus 1 minus 1 an minus 1. You'll get similar things all along. Here you'll get 10 minus 1 a1, and then the a0s will cancel. Now look at what you've got. This is 9, right? The next one in the series will be 99. This one is going to be a whole bunch of 9s. This one's going to be one more 9. It'll have another 9 there. So this is going to be all the 9s, all the 9s. They're all going to be 9s. So they're all divisible by 9. Okay, so I can pull out a factor of 9. So this is always going to be 9 times some whole number. If the cross sum is divisible by 9, this is divisible by 9, then this better be divisible by 9. And similarly, if the cross sum is divisible by 3, this is definitely divisible by 3, then this number, the original number, must be divisible by 3. So that's the proof. Dead simple, right? Dead easy to prove. Okay?
Why does that only work with 9s and 3s?
Precisely because the factor that you take out is 9. Okay? That's why. So, basically, you can only do it for 3s and 9s then. So there are a bunch of these rules, some of which are easier than others. We can go through them, right? So 1, okay, that's pretty easy to check if something's divisible by 1. 2 is easy, it just has to be an even number. 3s, we've done. What about 4s? Okay, what's the divisibility rule for 4? Okay, I'm going to write you down a multiple of 4. 1, 4, 5, 6, 3, 2. Viewers can check if that's a multiple of 4 directly. We know it is. How do we know it is? The way you do the 4 check is you just look at the last 2 digits. Okay, and you ask yourself, are the last 2 digits divisible by 4? If they are, that's enough. So here it's 32. That's divisible by 4. I don't need to worry about the rest. And it's easy to see why, because these are hundreds, thousands, tens, thousands. 100 is divisible by 4. 1,000 is divisible by 4, and so on. All the higher powers of 10 are divisible by 4. So the only thing you need to check are the last 2. So 4s are easy as well. It's a really easy test. 5s, pretty easy. Does it end in 5 or 0? Sixes, well, there you have to do the 2 test and the 3 test. Okay, so you check is it even, and then you do your cross-sum test for 3s.
And it has to pass both.
It has to pass both, yes. Sevens, we're going to come back to sevens. Seven is a notoriously magical and mystical number, right? And sevens are the hardest of these, of these sort of lower numbers for doing the divisibility test. So we'll come back to 7 later. Eights, let's try eights. Okay, so here's an example. 1, 7, 5, 2, 4, 6, 4. So again, viewers can check that this is indeed a multiple of 8 directly. How do we check it? Well, it's very similar to the 4 test, but it comes in an extra stage. Well, it depends how good your mental arithmetic is, actually. Okay, so what you do is, so whereas with 4s, we check the last 2 digits, with 8, we check the last 3 digits. Okay, so we look at this 464 and we ask, is that guy divisible by 8? If that guy's divisible by 8, then this guy is guaranteed to be divisible by 8. Again, why does it work? It's a very similar reason to the 4s. So basically because the thousands, the 10,000s and so on, and all the higher powers of 10 are automatically divisible by 8. So you only need to look at the last 3. But I don't know about you, Brady, but my mental arithmetic's not good enough to check straight away whether that number is divisible by 8. But there is a test for checking very easily whether, if you've got a 3-digit number, whether it's divisible by 8. Let's take this case 464. What we do is we take these 2 digits here, okay, 46, and we multiply that by 2, and then we add the other digit. Okay, if you do that, you get 96. Now, my mental arithmetic is just about good enough to know that that is a multiple of 8. Okay, so if this number is a multiple of 8, then this number is a multiple of 8, and by association, so is this number. So it's a 2-stage test. So let's just prove this 3-digit test for the multiples of 8. It's, again, quite easy. So we just take n, and the number that we're interested in, well, let's write it as 100 times a2 plus 10 times a1 plus a0. The test we're going to perform is, let's call it Tn, is basically we take, the first 2 digits, so that's like 10 a2 plus a1, okay, and we multiply that by 2, and then we add the other one, which is a0. Now take these 2 away from one another, and you get n minus Tn. What are you going to get? You're going to get 100 minus 20 a2s, that's 80 a2. You get 10 minus 2 a1s, that's 8 a1. And the a0s cancel. You can probably see it now, right? Basically, if this number is divisible by 8, which was the thing that was our test. So if the test number is divisible by 8, this is guaranteed to be divisible by 8, then that's going to be divisible by 8. That's why it works. Should we carry on?
All right.
Okay.
What else you got?
Well, we've done 9s already. So 10s. I think, most of us can work out 10s, living as we do in our base 10 world. So let's do the test for 11s. Dead simple, really easy test. Okay, so let's pick a number. This, you can check, if you use your calculator, this is a multiple of 11. Okay, so let's do the test. Okay, so the first thing you do when you do the 11s test is you have to reverse the number. Okay, so you reverse the order of the number. So you write it as 9, 6, 6, 5, 2, 0, 5. And now, you don't take the cross sum of this number, you take the alternating cross sum. What do I mean by that? Well, that means I do 9 minus 6 plus 6 minus 5 plus 2 minus 0 plus 5. Then I think it is, let's have a look, I think it's 11. Okay, so again, the rule is, if the number you end up with here is a multiple of 11, then the number you started out with is a multiple of 11.
So if it had been 22 or 30?
If we'd got 22, yeah, then we would have guaranteed the original number was a multiple of 11.
Gosh, that's really obscure. Like.
Yeah, we can prove it if you want. It's actually quite easy to prove. But there's another slight take on the card trick that you can do for this one. It needs you to be slightly quick with your mental arithmetic. So basically, you lay out a bunch of cards. I don't know, any order. Let's not worry too much about what it is. Okay, and I don't know, let's take a 5-digit number. Okay, so you want to start off with something that's not going to be a multiple of 11. Should we just check whether this one is or isn't just before we proceed? 5 divided by 11, which sod's law? No, it's not. Good. Just laid out a random number here. Okay, and now you're going to show how clever you are by you're just going to say, I'm going to add one card and make it a multiple of 11. Okay, so how do you do that?
I can't do that thing in my head, reversing and alternating cross sums.
Okay, let's see if I can do it. Okay, so it's, well, okay, it's a challenge, right? Okay, let's do it.
That is what you have to do.
You have to do it, yes, you have to do it, but you have to do it in your head. Okay, so I'm going to... Okay, so just have to get two.
Worst card trick
This
ever.
is rubbish, yeah. Okay, right, yes, I know what I need to add. Okay,
You need to add.
I need another card from over here. Yeah, okay, so I need to, okay. I think that should do it.
A 5 at the start.
Yeah, so if you've got if your mental arithmetic is better than mine, you'll do this in no time.
So you were reversing that number and then alternating.
Yeah, so I was doing the cross sum, the alternating cross sum in reverse, right? 5 minus 3 plus 1 minus 2 plus 4, I think is 5.
Right.
Okay, so I need to take off 5. That would get me to 0, which is definitely a multiple of 11, you see.
Oh, right, the 0, right.
So the goal is to get to a multiple of 11. You can also start playing around putting numbers at the start, but that gets a bit more complicated. But all right, let's try it, okay? 5, 4, 2, 1, 3, 5 divided by 11. Yay, it worked. Okay, so obviously you need to be pretty sharp in the mental arithmetic to do this one, which I'm afraid I'm not. 12s. 12s, well, 12s is just, you build it from the 4s and the 3s, okay? So it's the same as, you do the 4 test and then you do the 3 tests, so that's easy.
And that just has to pass both?
It has to pass both, yeah. We could go on, but let's come back to 7s, okay? Because we skipped 7s, which is a bit naughty. 7s are hard. 7s are notoriously hard. There is a reasonably simple one, but it also reminds me of a friend of mine. I got a friend called Norrie. Norrie is a lot of things, but he is not a mathematician. But he has this thing he can do where if he sees a number, he can tell immediately whether it's a multiple of 7. And it's really strange. He sort of sees the number in a cloud in his mind, and then if he's sort of warm towards it, if he feels like a friendship towards it, then that means it's a multiple of 7. This is totally real. This is totally real. He's not, as I said, he's not a mathematician. He did English at uni, but yeah, he has this rather unusual thing that he has.
How did you find out that he has this ability? How did that come up in conversation?
Oh, Norrie likes to talk about himself a lot. So it was always going to come up at some point.
Do you test him? Do you get out of camp?
He can do it. There's no messing about. He can totally do it.
How big a digit?
Yeah, so he can go up to about 5 digits, and then he starts to feel physical effects. Apparently, at that point, it's really unusual.
I should be making a video with Norrie.
Oh God! Well, the irony was, when I told him I thought I might mention this, he decided that the whole video should be about him. This is typical Norrie. But I said the whole video is not going to be about you, Norrie, but maybe it is.
Will he let us have a picture of him to put on the screen? Right?
Norrie will love to have a picture of himself on the screen.
That's Norrie there.
Yeah, okay. So how do I do it? Okay, so we got a multiple of 7. Let me write it down. If Norrie looked at that number, he'd start to feel his friendship feelings of warmth and all that, right? Okay, so the 7s test, the simplest one I could find is the following. You take the blocks of 3. Okay, so this block of 3 here, 984, and then we do like an alternating sum again. So we now take the next block of 3, which is this one, and we take it away, 976. And then we keep going like this. The next block is just going to be a 6. Of course, we stop here. Okay, if we had more, we'd keep doing this in an alternating way. Okay, so now you actually calculate this thing, which is obviously pretty easy to do. So that is going to be, I think, 14. So if the result is a multiple of 7, that guarantees that the original number is a multiple of 7.
I imagine quite often we're going to get negative numbers on this test.
That's fine. They can be negative numbers. It can be a multiple of 7. It's just a negative number times something. This was actually a really simple example, and it was pure luck that it turned out to be so simple. Normally, you're going to end up with a 3-digit number here, right? So you're faced with the question of, is that 3-digit number a multiple of 7, which generally is not going to be that easy. So let's do another example, maybe quickly, just to see how that can arise. Here I have another number which happens to be a multiple of 7. So I do 123 minus 872, and I am going to get this. It turns out to be minus 749. That's a bit hard, isn't it, Brady? That's beyond my mental arithmetic, that's for sure. Okay, so we're going to now do another three-digit test for sevens.
Is that really? But I mean, 749 actually is pretty easy.
Oh, that's really easy, yeah. Just realised. See, this is why I missed the Belfinger Prime thing, Wayne.
Let's pretend that is a hard.
Okay, let's pretend it's hard. But what would be the test that we'd do? Okay, so you take your 7. We don't need to worry about the minus sign. You take your 749. Okay, we take this number here, which is 74, and we take off twice this number here. Okay, so 2 times 9. Okay, that's 56. And then the issue is this a multiple of 7? Which of course it is. Okay, that would guarantee that this is, and by association, this is. This test for 3 digits is quite straightforward to prove. Proving that these blocks of 3 works is not so easy. You can prove it, okay?
I hope you can prove it, otherwise you shouldn't be using it.
You can prove it, and it relies on 2 facts. We're not going to do the proof. The first fact that you need to prove this is that this number is basically 7 times 11 times 13. Okay, so actually what's important about it is that it's a multiple of 7. The other fact that you need to know is that 999,999 is also a multiple of 7, and it's this multiple of 7. So this is a multiple of 7, this is a multiple of 7. These are the 2 facts you need to prove this particular sevens test.
But it's quite an elaborate proof.
It's exactly. It's not particularly entertaining proof. Notice, by the way, it's got this number in here. Do you remember that number?
I do. Isn't that the one where you can like cycle?
Yeah. We did a video on that number. In fact, I think we even probably showed that result. It sort of pleased me that reappeared. Okay. So you can do one in all generality. Okay. Which, I don't know how exciting this is, but we can do it with an example. Maybe.
What a way to test if any number is divisible by anything.
Any number that ends in 1, 3, 7, or 9. You might need to use a few iterations of it to actually get down to the bottom. But yeah, there is a general test. So let's do an example. Okay, so I can illustrate the general test.
Do you want another piece of paper?
Yeah, why not? So let's try it for 23. Okay, so the first thing that you have to do, so let's start with 23.
That's the number, the divisibility number.
Yeah, we're going to look at, we want to ask things in the 23 times table. The number we're going to test for is this number, which is in the 23 times table. So the test goes in various stages. First thing you've got to do is you've got to generate a new number from this guy. Okay, I'm going to call it the divi number. Okay.
From 23?
From 23, I'm going to generate 23's divi number. So the first thing you have to do is you have to multiply this by something to make it end in 9. Okay? So if you've got a number ending in 3, to make it end in a 9, you just multiply it by 3. Okay? So that will give us 69. So you've now got a number that ends in a 9. Okay? If your number ended in a 1 or a 7 or a 9, so it wasn't 23, it was 21 or 27 or 29, you would multiply by a different number to get it to end in a 9. Okay, it would still be one of 1, 3, 7, and 9, but you just choose something else. The goal is to get something that ends in a 9. Okay, once you've got something that ends in a 9, you then add 1. Okay, so that's easy. That gives us something that's a multiple of 10. It's guaranteed to be a multiple of 10. Okay, in our case, it's 70. Now, once you've got this multiple of 10, you just divide by 10. Okay, so let's divide this by 10. We obviously get 7. Okay, this is our divi number. So what's the test? Okay, so now we've got our divi number. We've got our number that we're interested in looking at. And so the thing you have to do is you have to write this number in the form 10t plus q. Now, if I do that, that means that t is 103 and q is 5. Now, using your divi number, what you do is you create, so let's call the divi number m. Okay, you create a new number, which is this thing. Okay, so let's calculate what this is. Okay, so m is 7, q is 5, and this is 103. That happens to be 138, which hopefully your mental arithmetic is good enough to check see that is a multiple of 23. So if the number you end up with here is a multiple of the 23, then the number you were testing is a multiple of 23. So you can adapt this method to any number that ends in 1, 3, 7, or 9, and it will work. Okay, what it relies on is that the number's constructed in this way. It's guaranteed that if something divides this number, then it will also divide this number. Okay, and you can easily prove that. Not too difficult to prove. Okay.
Not the easiest process to run through, but
no, it's not. But then it's applying to any number. But this is completely general thing now.
It doesn't apply to numbers divisible by 5. It almost applies to all the odd numbers, but not.
The idea is the goal is the challenge, of course, is you've got to get. It's very important that you get to this point where you have something that ends in a 9. That's what you need, and then so you can do this out of one business. Blah blah blah. Right. So that's important. Of course, that works with the 1, 3s, 7s, and 9s that you can do that for.
Do you like that?
It's general. It's not particularly. I mean, oh, come on. How good's your 23 times table, Brady? Exactly.
But do you look at that and think, oh, that's a cute trick, or do you think, oh, that was a bit of a mess?
If you want to know what I like about it is, so when I found out about it, I sort of immediately wanted to prove it. Okay, I wanted to see why it works. That's what, and I think that's true of anybody who's sort of into maths is, okay, it works, but why does it work? Let's prove it. You immediately sit down and prove it to yourself, and you understand why it works. And I think that's what I liked when I saw why it worked, which is in the proof. So I think we should leave the viewers to prove it, right?
Here we go. How many numbers below 200 have exactly 3 divisors? For example, 4 has 1, 2 and 4 itself, but how many more might exist? This is a new problem from Brilliant, today's episode sponsor. For a while I've been talking about Brilliant's problems of the week, but I'm excited to see they now have daily problems. I also like this one about chessboards and dominoes. Of course, Brilliant still has all their top-end courses and quizzes spanning all sorts of mathematical and science topics, and they're still offering 20% off a premium subscription to Numberphile viewers. Simply go to brilliant.org/Numberphile to check it out. There's plenty of free stuff on the site, but a premium subscription might be worth a look. And after today's video, I hope you might do well with questions like these ones. Our thanks to Brilliant. Go to brilliant.org/Numberphile for more information.
We need to do 6. There needs to be 6 rows here. 6, okay.
God, worst card trick ever.
It does take a bit setting up. Well, if you've got patient audience, you can do this.